Hello everybody. So today's topic of lecture is buffers, especially to say biological buffers in the course of biochemistry. So buffers, as the name implies, what does it mean? So buffers, we used to say it maintains a constant pH. In case of biochemistry, we used to say it maintains a constant pH. What do we mean by that? So it means that it resists a change in the pH. So how does it resist the change in the pH? It resists the change in pH. How does it resist? Either on the addition of acid, or on the addition of base, either on the addition of acid or on the addition of base. We call these processes as, so this one is H plus and this one is OH minus. This is called protonation and this is deprotonation. Normally, buffers are physiological fluids that are maintained in the living system itself. But universally, we consider water as a weak buffer. Okay. So, but coming to physiological conditions, we never use it to say water as the most effective buffer. So, we can compare the buffer action of a fluid with that of the water. So, water has its own buffering capacity. It satisfies these conditions. Either it gives you these protons or it provides you these OH minus ions. Both of these molecules gives you the molecule formula, water formula H2O. And we can also define this buffer in terms of chemistry. And how do we define on that? It consists of mixture of weak Bronsted acid. I think we have discussed in the other video. If you don't know what we mean by Bronsted acid, just check out that video. In Henderson-Nasselbatch equation principles, I have discussed about Bronsted acid as well as weak acids also. So it consists of a mixture of weak Bronsted acid and its conjugate base. So both these terminologies have been described in that video. Please check out that video if you don't know about what you mean by weak Bronsted acid or conjugate base. So for this we can example, there are many examples for buffer. So the universal example, we'll take it as acetic acid. So acetic acid, mixture of acetic acid and sodium acetate. Mixture of acetic acid and sodium acetate. This comes under the topic of acid buffers. So buffers are of two types. One is acid buffers, because this buffering action is done under the acidic conditions. These are known as acid buffers. And the other type is basic buffers. And by example for this one is, so any basic solution that has the potency to maintain the constant pH. The example for this is mixture of ammonium hydroxide and ammonium chloride. Okay, so in these two things, the acidic buffers is acetic acid acts as acid buffer, ammonium hydroxide acts as a basic buffer in these solutions. Okay, so acid buffers is a combination of weak acid and its salt with a strong base, and it's salt with a strong base, that is called acid buffer. The weak acid is acetic acid and salt with strong base is sodium acetate, where acetate is the strong base there, or sodium. And in case of basic buffers, and for acid buffers, there are other examples also we can consider, because these are going to be explained in biological buffers. I am going to explain about that. So other examples of acid buffers, H2CO3, that is carbonic acid, and sodium bicarbonate. This is the buffer that acts as in the blood. That's why I indicated in the red color, even though I'm going to represent other examples also in red color. So bicarbonate as well as sodium carbonic acid and sodium bicarbonate. And the other example, phosphoric acid and sodium monobasic phosphate. This is the other example, and I'll write it down here. Third example is formic acid and sodium formate. Okay, HCCO. So these are the examples of acid buffers: carbonic acid and its sodium bicarbonate, phosphoric acid and sodium monobasic phosphate, and formic acid. So these are the examples of acid buffers. Now we have come to basic buffers. What do you mean by basic buffers? Now this is a combination of weak base and a salt with strong acid. Now you can know the differentiation between acid buffers and basic buffers. In acid buffers, I told it is a mixture of weak acid and its salt with a strong base in the sense sodium. And in case of basic buffers, this is a mixture of weak base and associated with the salt with strong acid. So ammonium hydroxide is a weak base, and the salt with the strong acid is ammonium chloride. So chloride acts as a strong acid, etc. So these are the examples for acid buffers and basic buffers. And even more for basic buffers, there are certain examples, other examples. Ammonia and ammonium chloride. Ammonia, ammonium carbonate. Ammonia and ammonium carbonate. Okay. Now these are the types of buffers that exist in organic chemistry as well as biochemistry. And apart from these two categories, acid buffers and basic buffers, there exists a third category. Okay, and it is known as double salt buffers. Double salt buffers. So double salt buffers. This is a special case of buffers. Double salt buffers. And what do you mean by double salt buffers? First of all, I will tell you the example of double salt buffers. It is phosphate buffer. Phosphate buffer is the double salt buffer. And what do you mean by double salt? Why it is called as double salt? Because this buffer system is comprised of two salts. This buffer system consists of two salts. Let me explain in phosphate buffer. In phosphate buffer, there are two salts are present. The first one is two salts means for each and every weak acid or weak base, there is excess salt in case of acid or basic buffers. But in case of double salt buffers, it consists of a weak acid or weak base, but it comes along with it mixture of two salts are present. And what are those two salts? In case of phosphate buffer means first salt is monobasic potassium phosphate. Monobasic potassium phosphate. And it is now written in the formula KH2PO4. This is monobasic. Okay, H2PO4. This is called monobasic because it has the tendency to promote only monobasic. And second one is dibasic potassium phosphate. Dibasic potassium phosphate. And the formula is K2. See, this is monobasic and this is dibasic. K2. There are two potassium molecules that are linked to the phosphate. That's why it is being reduced to single hydrogen ion because of the substitution of two potassium atoms here. So this is the example of double salt buffers. So anyway, you are going to see this explanation in case of biological buffers because this buffer is a extracellular buffer present in the physiological conditions that promotes in two ways and a buffering action, whereas normal buffers gives you only either with a single salt, but it has two salts, so it can be more efficient in maintaining the buffer. Okay. Now we are going to see the next topic, buffers and titration curves. So in the last class under Henderson-Hasselbalch equation, I have explained you this titration curve with an example, with acetic acid buffer example, and its pKa. Here, it is the same titration curve, but I am going to show you with the three examples in a single titration curve. Now just I have mentioned you about acid and basic buffers, and I am going to explain all those buffers in a single titration curve so that you can get an idea for different solutions. If you have to maintain a constant pH, you have to consider different buffers depending on the pH of that solution. So in order to know that, here you have considered three weak acids. Okay, so three weak acids. One is acetic acid, second one is phosphate, and third one is ammonium ions. Now you can see in this example, the first one which I have already mentioned, the acetic acid. So acetic acid, and I told this point as equivalence point where pH is equal to pKa, and what do you mean by pKa? Both its salt and conjugate base are present in equivalent amounts. Now in case of acetic acid, the weak acid and its conjugate base, acetate, they are present in equivalent amounts under what pH? In pH 4.8. I told you that 4.8. Now for this pH, the buffering action would be in between the range of 4.26 to 5.26. So the pKa action, where pKa is equal to pH, and the pKa value for acetic acid is 4.76. Now you can see the difference of buffering range. So it is 4.26 to 5.26. So that is nothing but It is simply a range of 0.5 plus or minus 0.5 pH units, plus or minus 0.5 pH units. So 4.26 plus 0.5, 4.76. So it has the most effective buffering action in this range, 4.26, either from this range, this range, let me delete this, so this range, and 5.26 is this range. So in this range you can see the curve, how it gets tilted. So there is a shifting point. This is called a off equivalence point. So this is the equivalence point, this is off equivalence point, and this is another off equivalence point, where the shape of the titration curve is shifted from one direction to another direction. The momentum change is high at this place. What do you mean by momentum? The shift in the direction of n vectors. Here we consider the pH as a vector. So pH equivalence, as you are keeping on adding acetic acid in these conditions. So there is a shift at the off equivalence point where 0.426, where it gets saturated until 5.26. This is the saturating point for an effective buffer to maintain a constant pH. So that rise in the range of 0.5 pH units apart from 4.76 pKa of acetic acid. So 4.26 and 5.26. This is the best buffering action range for acetic acid. So you can consider whichever solution if you want to maintain under these range conditions. Okay. So this is called buffering region. Similarly for other acids also, similar for other buffers also, it has its own buffering range. Okay. If you consider for second one, that is phosphate buffer, and the phosphate buffer pH is equal to pKa, that is the equivalence point is 6.86. So you have to add plus or minus 0.5 pH units. If you subtract 0.5 pH units, it will come 6.36, which is nothing but this value. And if you add 0.5 units above 6.86, it will come 7.36. So this is the buffering region for phosphate buffer to maintain solutions. Almost all physiological solutions in our body maintains under this pH conditions. So in our physiological system, this is the most effective buffer in extracellular region or intracellular region. This phosphate buffer is the main pH buffer that exists in a living environment within the body of an organism. The third acid is ammonia. So ammonia has its buffering action. So I have told this phosphate buffer under the condition of basic buffers because it contains phosphate buffer in the condition of double salt buffers because it contains two salts. See, this is monobasic phosphate because monobasic means here single potassium will come, and this one is dibasic potassium phosphate, and its conjugate base only it is present here, but you can see there are two salts. This is also one salt, this is one salt, but in acid buffers you are seeing only one conjugate base. Here you are seeing two conjugate bases. That's why it is known as, this buffer is known as double salt buffers, DSB. Okay, and the third category, third example is ammonia. So ammonia has a pKa value of 9.25, whereas the pH range is also at this equivalence point, it equals here. So buffering action of pKa of ammonia is 9.25. So you have to add plus or minus 0.5 pH units for the effective buffering range action. So the shift is from here to, and 9.25 means 9.75. So 9.75 to and 8.75. So ammonia 8.75 to 9.75. So this is the within the range of plus or minus 0.5 pH units. So this is the buffering region for ammonia, and the base equivalents and the acid equivalents present in this ammonia are ammonium ions with the extra H plus ammonium ions, and as well as ammonia acid, it is a base. So these are the conjugate base acid or conjugate acid base equivalents of this ammonia buffer. Now these are the three examples in the titration curve to show you the effective range of buffering condition for these buffers. Now considering the buffer action, there are two factors that determine the effectiveness or capacity of buffer solution. So effectiveness of buffer solution. If you consider the effectiveness, in order to have an effective buffer action, there are two factors involved. Effectiveness of buffer action, there are two factors involved. The first factor, what is the first factor? The first factor is molar concentration. Molar concentration of what? Molar concentration of buffer components. Buffer components. And what are those buffer components? It is the weak acid, that is the salt, and the conjugate base. Weak acid, salt with its conjugate base. Those are the buffer components, and their molar concentration plays an effective role for effective buffer action. And the second one is conjugate base, relative concentrations of weak acid and conjugate base. So I'll explain you with an example. For example, you consider, first of all, we are talking about molar concentration. So you have to preparing a buffer, acetic acid buffer, so acetate buffer. So you have preparing 0.1 molar acetate buffer, 0.1 molar acetate buffer. So this molar concentration has to be more effective in order to provide effective buffering range. And how can it give effective buffering action? If the the buffering components are present in an equivalent amount, then this acetate buffer can give you the effectiveness of buffering action. And what are those equal components that has to be present? It is 0.05 mole of acetic acid. So weak acid has to be present in 0.05 moles, and the remaining half has to be its conjugate base, acetate. So if these two molar components are present in an equivalent amount for an acetate buffer, that is 0.05 plus 0.05, that gives rise to 0.1 molar, then this factor will provide you the effective range of buffering action. Okay, and how would you determine that? Okay, so this 0.1 molar acetate buffer, now coming into practical terms, if you go for biochemistry practicals, how would you prepare this 0.1 molar acetate buffer? So it contains 0.5 molar of acetic acid, so you have to prepare 0.05 moles of acetic acid. And how will you prepare the acetate? Instead of preparing acetate, you are going to prepare 0.05 moles of sodium acetate. That will give you the conjugate base acetate, sodium acetate. CH3COONA. Now this gives you the 0.1 molar acetate buffer. So you are going to dissolve in 1 liter water. We have talked about the factors for an effective buffering action. Now the next topic is the important topic relevant to biochemistry, that is biological buffers. So what are the biological buffers present in our system? Now this tabulation will tell you the buffers present in the components, that is in extracellular fluids, bicarbonate buffer and protein buffer is present. In intracellular fluids, phosphate buffer and protein buffer is present. In erythrocytes, within erythrocytes, hemoglobin buffer is present. That is, intracellular fluids means in all the cells, in all kinds of cells, phosphate buffer and protein buffer is present, including RBC. But especially in RBC, there is a special type of buffer is present that is known as hemoglobin buffer. And these kind of buffer systems, especially if we are concentrating mainly on the blood pH. So because blood is considered to be the main traffic highway of the body. So it is a fluid connective tissue. So it has to, if you can't, the buffering action plays a central role in blood pH. So our body has developed 3 lines of defense. Okay, there are 3 lines of defense to regulate this body's buffering action regarding acid-base balance to maintain that blood pH. So there are 3 lines of defense. And what are those defense? Number 1, blood buffers. And number 2, respiratory mechanism. And number 3, renal mechanism. So these 3 places are where our body has a frontline defense in order to maintain a constant blood pH. Blood buffers, respiratory mechanism, and renal mechanism. Blood buffers takes place within the blood, and respiratory mechanisms, it takes place in exchange of partial O2 and partial CO2 within erythrocytes, that is this hemoglobin buffer within RBCs, that is a respiratory mechanism from exchange from the lungs to into the tissue of blood, that is capillary tissue. And the third one is renal mechanism, which takes place in kidneys. So whenever we excrete, we tend to lose out a large amount of acids by the way of protons or any acids that visit to excreted through urine. So severely it affects the pH of that urine. So in order to maintain that, it has a mechanism, renal mechanism, which ultimately, because kidney is the place where your blood gets purified. So if there is an excess of H plus ions or OH minus present in your blood, it should be removed out effectively through not only through buffering action and in a physiological mechanism also through renal mechanism. So where your kidney purifies out by providing sufficient amount of water or solutes, it is called a water retention. Water or either way solutes, it's how body mechanically maintains the blood pH through kidneys. And if you consider this blood buffer, it contains 3 buffer systems. This blood buffer contains 3 buffer systems because we are mainly focusing on blood buffer only. So blood contains 3 buffer systems. Number 1 is bicarbonate buffer. Second one is phosphate buffer, and the third one is protein buffer. So these are the 3 buffer systems that are present inside the blood. So bicarbonate system, it is the exchange of sodium bicarbonate and carbonic acid in order to maintain effective pH. This results from dissolved CO2 as well as gaseous CO2. So these are the 2 things that will play a central role which affects the blood pH, and it is effectively maintained through its acid. So CO2 plus H2O, what it gives rise to? It gives rise to, that is, dissolved CO2. So whenever you respire, you inhale gaseous CO2, and that gaseous CO2, depending on the partial pressure of capillary tissues, it gets dissolved in the blood. That gives you the dissolved carbon dioxide, and this dissolved carbon dioxide mixes with water in order to form carbonic acid. And this carbonic acid, depending on the conditions, either this concentration will increase or decrease to maintain a constant pH of 7.4. That is what we call bicarbonate buffer. And the second one is phosphate buffer. This phosphate buffer, it exists in all the cytoplasm of the cells. Cytoplasm of cells. So it is an intracellular buffer where H2PO4 minus. What is H2PO4 minus? It is monobasic potassium phosphate. So monobasic potassium. This acts as a proton donor. And HPO4 2 minus. This is what? This is dibasic phosphate. And this is monobasic. This is dibasic. This dibasic phosphate acts as a proton acceptor inside the cells. Okay. So effective buffering action for this is. So regarding phosphate buffer, the pKa value of phosphate buffer is 6.86. In case of bicarbonate buffer, I forgot to tell you what is the effective range for bicarbonate buffer. It will be around 7 only. That is the blood pH range. So it will be around 7. In order to maintain effective buffering action for blood, this bicarbonate buffer, these two components has to be maintained in the ratio of 20:1:20. So 20 parts carbonic acid and 1 part sodium bicarbonate, that is carbonate. So this ratio has to be maintained in order to preserve the blood pH 7.4. Okay, in this ratio it has to be maintained. Now coming back to phosphate buffer, I told you its pKa range is 6.86 and it has a buffering region. What I have explained in the titration curve, it will have a buffering region. So the effective buffering region for this phosphate buffer is between 6.4 to 7.4. So whichever solutions that are present in this range, this phosphate buffer effectively maintains that constant pH. So you can see all our body fluids or components, even enzymes, they exist within this range only, 6.4 to 7.4, where the pKa is close to around the phosphate buffer, which is nothing but 6.86. So it resists the pH changes in this range between 6.4 to 7.4. And in blood also, apart from bicarbonate, this phosphate buffer also effectively maintains the blood pH also, because it can go up to 7.4. So how much is the concentration of phosphate in blood? It is about 8%. So phosphate buffer exists in blood plasma about 8%. Okay, so in whether of the buffer and bicarbonate buffer, this buffering action also. So we are seeing all these three types of buffer regarding maintenance of constant blood pH. So phosphate buffer also plays a central role there. And in case of for blood, it is, you know that the pH is between pH is exactly 7.4, and phosphate buffer, we told its buffering action is between 6.4 to 7.4. But I told that it is present predominantly in the cytoplasm of cells. So our intracellular fluids, what is its pH range? Our intracellular fluids, the pH range is between, the pH range of intracellular fluids is, it is around 6 to 6.9, 6 to 6.9, which is nearer to the pKa of 6.86 of phosphate buffer. Okay, so phosphate buffer is then in blood it is 8%, but in case of within the cells it is present in high levels. So inside the levels, phosphate buffer is present in high levels. And in case of renal systems, I have told you that renal mechanisms. In renal mechanism also, this phosphate buffer acts as a central role by the elevation of its components in the urine and renal distal tubules. Urine and renal distal tubule. And we know that in renal part there are two tubules present, proximal and distal. And in distal tubule, this phosphate buffer is present in elevated levels in order to maintain a constant pH. So that is the working action of phosphate buffers. last one is protein buffer, and it can also, within this category there exists another category which is known as amino acid buffer, which you are going to study in detail under the concept of protein structure and those things. Amino acid buffer. So this system operates in, and especially for humans. So amino acids contain both this basic part as well as acidic part. So the name itself implies it is a buffer. So the amino part is comprised from amino group and the acid part is from COOH group. So we know the general structure of amino acid. It is 9H2, the C combined with the alkyl chain, and then the acid part. So amino acid buffer system. So these protein buffers are very important. Where it is very important? In plasma, blood plasma, and intracellular fluids. So it is the main component system acting on plasma as well as intracellular fluids. So it provides conjugate bases in a general term known as PR minus. So it consists of several amino acids, maybe basic amino acids such as arginine, lysine. These are the basic amino acids that are present in amino proteins that will give you a conjugate base notated in the form of PR minus, which will and in case of conjugate acid, so this is a weak base because protein buffer acts, it is a basic buffer. The protein buffer is nothing but a basic buffer which exists in the range of above pH 7. So that's why it is known as basic buffer. Then protein buffer, any buffer contains two components, right? Regarding basic buffer, it should contain weak base, and the weak base is this PR minus, and that conjugate acid is HPR plus. HPR. It is conjugate acid. So it is not a single protein, means it contains many amino acids. So those amino acids are represented as PR minus, that is weak base, and conjugate acid HPR. We could not name a single amino acid and tell it as a protein buffer. It consists of several amino acids. So generally we are telling it as PR minus as weak base and HPR as conjugate acid. So this is the example of protein buffer systems, and in case of amino acid buffer we are going to study in detail under the heading of proteins and amino acids. So here we don't want to bother about that. And if this buffering action by default it takes place in a control level, when the body goes out of control, it results into a disorganized condition which results you in various diseases. And regarding the out of control, this acid base equilibrium, our body results in two conditions. The first condition is known as acidosis, and the second condition is known as alkalosis. Especially we are telling in terms of blood only. So in terms of blood buffering action, so in case of acidosis, if the pH of the blood goes below 7.34, if the blood pH drops below 7.34, then this will result into acidosis. If the blood pH shoots above 7.46, see the minute pH 7.46, it results into the condition of alkalosis. That's why you can see the accurate pH representation in terms of two decimal places, that is 7.34 and 7.46. So it has to maintain at this within these stringent levels. So it has to be maintained in a very stringent level. That's why in order to maintain the effective blood pH, all these buffering systems will play a central role in order to maintain this stringent sensitive pH between 7.34 and 7.46. So if the blood pH shoots above 7.46, it results in alkalosis. and you can see various symptoms resulting from that. It will result in high fever, and you will a vomiting sensation known as nausea. These are the conditions that will result due to alkalosis. Under these conditions, your doctor will prescribe in order to lower that pH of the blood. He will provide you antacids. So this is the treatment generally given for alkalosis treatment in a day-to-day life whenever our blood shoots out. So this is the overall picture of buffers. Okay, so I have to mention you about the types of buffers and the titration curve that exists in the buffers, and the different components of biological buffer system that is present in the body, and if this buffer system fails to maintain the constant pH in blood, and what it results. So this gives you the overall picture of buffers at a basic level. Thank you.